Hello everyone, I'm Dr. Vaibhav Pandit and today we are going to discuss the doubts related to your topic titled Image Compression Models. So this is the topic belonging to the subject Digital Image Processing or simply Image Processing you can call. Several of the topics we are already dealt with for your doubts, especially the fundamental image processing task. Those are the image enhancement we have addressed, the image enhancement into the spatial domain as well as image enhancement into the frequency domain we have been dealt so far, then image restoration, color image processing, then wavelets and multi-resolution analysis, and now here we are going to deal with the image compression through this particular topic. So based on to the image compression models, I will first of all take a practice of the two problems so that the concepts will be getting cleared with the practice of whatever the problems usually comes to the examination, and later on if any doubts are there regarding the concept originally for the image compression models or simply a single model if you talk about, I will also deal with that topic. So here we go with the problem 1. So we are having the problem statement. The problem statement is divided into the two parts here. So here we have part A and part B. So let us have the part A. The part A statement starts with a 256 by 256 pixel digital image has 8 distinct intensity levels. What is the minimum number of bits required to code this image in a lossless manner here? This is the first part. Now, you see here in this problem statement, the given information is regarding a digital image for which the dimensions in terms of pixels are given to us. So it means that we have 256 times rows by 256 times the columns here. So which forms a digital plane in which the image information is stored or maybe communicated further, and that has, as per the problem statement, the 8 distinct intensity levels. We are asked this question: what is the minimum number of bits required to code this image in a lossless manner? See, this is the topic of image compression. In the image compression there are practically the two cases, so that is the lossy and that of the lossless here. So here we have been asked to consider the lossless condition here. Surely we shall answer this particular question. Before answering this, let us complete the problem statement here. The problem statement is having the two parts. This was the first part denoted by part A here. We shall have the part 2 here, that it is denoted by part B here. So part B statement is one of the objective measures of the image compression is peak signal to noise ratio, that is abbreviated as PSNR. The continuation is the original and the reconstructed image are given below. So here we have been provided first of all the original image. You see here 4 rows and 4 columns. A representation in matrix form here we have for the original image. Similarly, we have the reconstructed image as well. The reconstructed image is also having the same order of 4 rows and 4 columns here, and further we are asked to calculate the PSNR expressed in terms of the decibels here. So this is what part A and part B here. Now in this problem statement we accompany more two parts. These are the part C and part D also. So these also we shall consider. So part C is To compute the entropy of the image is provided to us. The image is denoted f of m comma n, that is equal to, here again a matrix of the order 4 by 4, and last the part D here, that is prove that entropy is maximum when the symbols are equiprobable. So this is our complete problem statement here. Now one by one we shall have a solution to parts A, B, C and D here. Now let us recall what was the part A statement here. In the part A statement, we have been provided a digital image of the dimensions 256 by 256 with a consideration of 8 distinct intensity levels. The exact question is, what is the minimum number of bits required to code this image in a lossless manner? So to answer this particular question, as we have to focus on the 8 distinct gray levels. See, the coding of the 8 distinct gray levels can be, as such, we represent it mathematically. It is basically log to the base 2 for how many number of gray levels we are having consideration as the environment of representing the image here. So here we are representing the mod of log to the base 2 over the 8. 8 is the number of distinct gray levels for the image representation and further coding decoding purposes here. So this will result into the value 3. So this 3 is nothing but 3 bits per pixel the representation. So this information if we use, so in general we have 2 to the power 3 is equal to 8. The total 8 distinct gray levels here. So if we multiply the 3 bits per pixel to whatever the order we obtain just by multiplication of the two dimensions, 256 by 256 by 3 here. So that is the total number of bits required to code the given image, and this calculation comes out to be, we have here 1,96,608 bits in total. Now this was the part A answer. Now you can also underline what the answer we have obtained here. With the given information into the part A of the problem statement, we have this answer. Now we come for a focus on part B here. We just recall what was the problem statement here. So part B, one of the objective measures of the image compression is PSNR, that it is peak signal to noise ratio, and we had been provided the original image and the reconstructed image both of the order 4 by 4 here, and we have been asked to make calculation for the PSNR performance matrix, and that is expected to be computed in terms of the measurement of decibels here. So to find solution to this particular answer, we require a mathematical expression, that is computing PSNR value in decibels here. So as we expect the answer in decibel, we will have 10 log to the base 10 to whatever the logic we built here. See, the mathematical logic to compute the PSNR depends on the mean square error, that is represented in abbreviated form as MSE here. So here we have the formulation. See, for decibels we write 10 log to the base 10 of, here we have a ratio in the numerator 2 to the power b minus 1. The complete bracket is having the power of 2, and that is divided by the MSE. So MSE is representing the mean square error. So this is basically the parameter measured between whatever the reconstructed image is there and the original image is there. So what exactly the MSE, the mean square error is? So mathematically the formula we can give as MSE is equal to 1 by the order. Here we have the dimensions multiplied, both the dimensions, capital M by multiplication 2, the curly bracket that has a square of the difference, where first of all we have f of m comma n, the original image representation, and f cap of m comma n, here it is the representation of the reconstructed image here. So I have already explained you what are the f of mn and f cap of m comma n here. So now the thing is to have calculation of the mean square error, that it is MSE. So we shall be making the use of this particular formula. Now in this particular problem, if you see the matrix, those are representing the original image and the reconstructed image. So we can make a substitution that capital M and capital N values both are equal to 4. So if we have a substitution to the earlier formula to compute first of all the mean square error, which will help us to have the computation of the intended PSNR, peak signal to noise ratio. So MSC formulation, MSC computation will be like this here. So we have MSC is equal to 1 upon, we have the multiplication of both the dimensions capital M by capital N. So here it is 1 upon, here we have 4 into 4 here. Now thereupon we have a square of the difference between the two images, that is the original and the reconstructed. So here we have the difference pixel wise here. So the first term inside the curly bracket will be a square of 1 minus 2. This will be further added by the square of 8 minus 8, added by the square of 6 minus 8, 6 minus 7 square, 6 minus 6 square, 3 minus 3 square, 11 minus 12 square. Then we have 8 minus 8 square, 8 minus 5 square, 8 minus 4 square. We have 9 minus 9 square, then 10 minus 1 square, 9 minus 15 square, 10 minus 9 square, 10 minus 11 square, and lastly 7 minus 9 square. So here you see there are 8 entries into the upper row. So all these are the 8 entries, and next to that in the below row here we have again the 8 entries. So total 16 entries here we have. So both for the original and the reconstructed image sample that is provided in the problem statement, we have the order 4 by 4. So total 16 pixels are there. That is why in the formulation of the MSE we have all these 16 entries in the curly bracket here. So now if we simplify this computation, so by the next line 1 upon 4 by 4 we can replace by 1 upon 16, and inside the curly bracket the computation of the differences and further squares of the same will lead us 1 plus 0 plus 4 plus 1 plus 2 times 0, then 1, 0, 9, 16, 0, 1, 36, 1, 1, 4 for each of the differences squared in the above step here. So finally the addition of all these 16 entries and the average, of course here this is all divided by 16 will give us the value. Here we have MSE is equal to 9.6875 here. So now in this particular problem statement, to use this particular value for the computation of the PSNR, the PSNR formulation just now I have shown to you people that uses the MSE into the denominator here. So in that particular formulation we have to also put the value of capital B, which is at the power place of 2 here in the numerator here. So here we substitute capital B is equal to 4 here. So we have the capital B, we have just calculated MSE value. So both if we can put into the formulation of the PSNR, so the computation will be like this. So here we have PSNR is equal to obtain the value into the decibels, we have 10 into log to the base 10 multiplied to the ratio where numerator is 2 to the power 4 minus 1 squared, whereas in the denominator we put the value of the MSE that just now we have computed. So all this is going to result into the value that it is 13.7, and here we represent the value in terms of the decibels here. So this is the answer for part B of the problem statement. So initially we had the 4 parts to the problem statement here, A, B, C and D here. So this is the solution for part B here. Now we need to find the solution to part C here. So recall back what was the problem statement for part C here. So in the part C, we were asked to compute the entropy of the given image. See, the given image is represented f of m comma n, and here it is of the order 4 by 4 again. So we have 4 rows this way and 4 columns. So the total 16 pixels here we have in this particular image sample, and we have to make a computation for entropy. See, entropy is one of the quality parameter. If you have the entropy of the image sample at the highest value, we can say that the given image is rich into the information here. So now, for the computation of this particular entropy, let us count what are the gray levels provided into the image provided as f of m comma n. So now you see in the first row we have 0 1 0 0. So we have the two levels, one is 1 and the another is 0 here. Now if you see, we have 2, we have 3 here. So in total we have the 4 gray levels, those represent the 16 pixel values here. So the total number of gray levels into the input image are, we have 0, 1, 2, 3 here. Now we shall follow the step number 1 before making a computation of entropy, because entropy requires the information of the probability of occurrence of any of the event. In the probability theory, here it is the probability of occurrence of the gray level here. So the probability of occurrences of all these 4 gray levels we have to compute. So first of all, for the gray level represented by 0 here, so we have the probability of occurrence of gray level 0, that we denote it as small p in the bracket 0, and that value you just count how many number of times there it is 0. You will come to see in the first column there are 3 occurrences, and in the first row here we have after excluding one common entry here, we have 2 more. So total we have 5 entries. So we have the probability of occurrence of the gray level 0 as represented 5 divided by 16. In the similar fashion, here we compute the probability of occurrence of the gray level 1. So for gray level 1, the probability of occurrence here we denote as P of 1 here. So you just count how many number of times 1 it is there. You will see in the first column only one entry is there for the value 1, whereas in the second column we have the 3 entries. So the total there are 4 entries. So here we divide the 4 by 16. So it will give us the probability of occurrence of the gray level 1 here. Now in the similar fashion we have to make a computation for the probability of occurrence of the gray level 2 here. So if you compute how many number of times, if you count how many number of times the value 2 is there in the given image sample, you will come to see that there are 5 entries of 2 here. So we have in the second column, third column and the fourth column the total 5 entries here. That is why we represent the ratio as 5 by 16 here. And at last we require the probability of occurrence of the last gray level, that it is 3. So we have it represented P of 3 here. So here it is the representation P of 3, probability of occurrence of a certain gray level. The gray level value is represented inside the parenthesis. Similar is the case in the earlier representation as well here. So there are the 3 values only 2 times, that is why we have the representation 2 divided by 16 here. So in the first step we have a computation of the probability of occurrences of all the possible gray levels as represented from the given image sample here. Now the second step and the last step is just to have computation of the entropy value here. So what is the formula that we can make use of here to make the computation of entropy, and by what particular symbol the entropy is denoted? See, the usual notation for the entropy is capital H here, and the formula it is given H is equal to negation of, we have the summation for the index variable I ranging from 1 to capital N, and here we have for the multiplication of p suffix I with log to the base 2 p suffix I, and that is all there in terms of beats per pixel here. So let us make the substitutions of whatever the probability of occurrences that in general we can denote p suffix I that we have already done into the previous step. So just the substitutions will give us the capital H to the form where we write minus sign as it is outside, and then the summation here we arrange. So we have here p suffix I into the log to the base 2 of p suffix I. So the first probability of occurrence that it was 5 by 16 multiplied to its logarithmic form having the base 2 here. We have 1 by 4 multiplied to the log to the base 2 of 1 by 4. Similarly, for the third place, here we have 5 by 16 multiplied to the logarithmic form to the base 2 of 5 by 16. And lastly, 2 by 16 into the log to the base 2 of 2 by 16. So we represent all this in terms of beats per pixel or beats per symbol also you can treat here. Now, this computation of the logarithmic values and further multiplication with the coefficients represented and the addition of all these four terms here will give us the entropy as denoted capital H. So capital H is equal to 1.924. This is of course in terms of bits per symbol. So this completes the solution to the part C of the problem statement. So out of the four parts here, now here we are completed with the solutions of the three portions here. Now we are left with the last one, that it is part D here. So coming back to what was the problem statement here. So here it was a statement for part C that we have already solved. The answer is H is equal to 1.924 bits per symbol, and now we have the last part to solve. In the last part we have been asked to prove that entropy is maximum when the symbols are equiprobable here. So let us have the solution to this particular part here. Answer to the part D here. Now in order to prove this particular statement, the statement is entropy is maximum. See, the entropy formulation we have just seen. Entropy depends on the probability of occurrences of the gray levels to represent in the image here. So we want the entropy represented by capital H to be a maximum, and this comes when the symbols are equiprobable. See, the probability is equal there. So that we have to prove here. So in order to prove the fact that entropy is maximum when the symbols are equiprobable, we have a consideration of the two cases here. So the first case we will say that the symbols are equiprobable, and in the second the symbols are not equiprobable. So both the cases we will try to have a consideration of, and then we'll validate the results that we already know. We have to just prove the same. Now we will have the calculation of the entropy in both of the two cases here, and then we can find that entropy is maximum if the symbols are as like the case 1, that is they are equiprobable here. So let us have the consideration of the first case. Here we have case 1, computation of the entropy for equiprobable symbols here. Now from the image sample that we have been provided in the previous also, that it was of the order 4 by 4 here, as only one sentence is to be proved here in this. For simplicity we will be selecting the image sample of the shortest dimension here. So let us have the consideration of the image sample of the order 2 by 2. So we have denoted it to be by small a, and it is a matrix form representation. In the first row we have the pixel values 1 0, and in the second row we have 0 1. So the 2 by 2 order image sample we have a consideration here for the case 1. So now the symbols or the gray labels are only the two here. So you see in this particular representation, either we have the representation of 1 or the representation of 0 here. Now we have the order 2 by 2 1 here. Now again we shall follow the two steps here. The first step is to just compute the probability of occurrence of the gray level, and the second step is to apply the formulation of the entropy here, where we can substitute this probability of occurrences here. So we have only two gray levels or the symbols here. So first one is the 0. We write probability of occurrence of the gray level 0, that we denote as P of 0, you see, and we have just counted it, that it is 2 divided by 4, so which we can reduce to the ratio represented by 1 divided by 2. In the similar fashion, we can have the probability of occurrence of the second gray level, that is the value 1. So we have denoted as P of 1 here. So this is equal to again 2 out of the 4, that we can have a reduced representation to the ratio 1 divided by 2 here. So the probabilities of occurrences of both the gray levels are there. Now we can have the substitution of it to the formulation of the entropy computation here. So entropy we have been representing by capital H here. We can also represent it as H of S. So H of S is equal to, we have the summation, the index variable I is ranging from 1 to capital N, and this summation is over the multiplication of Pi into log to the base 2 of 1 upon Pi, here it is, in terms of the beats per symbol here. So this is what the formulation to make computation of the entropy, that is denoted by capital H here. So in the given or the considered representation of the image sample of the order 2 by 2, where there are 2 times the pixel value 0, 2 times the pixel value 1 here. So we have H of S is equal to, we have P of 0 into logarithmic form of the ratio 1 upon P of 0, that is added to P of N multiplied to the logarithmic form to the base 2 for the ratio 1 upon P of 1 here. Now as we have both the values here, we have P of 0 to substitute in these two places, we have P of 1 as well to substitute in the corresponding two places of the second term here. So we get it to the form, we write H of S is equal to 1 upon 2 log to the base 2 of 1 upon 1 by 2, and the same is to be repeated in the second term here. Now we get it to the representation in the modified form, where we write this one here, you see the RHS, the modification in the logarithmic representation here, and as you see log to the base 2 of 2 is of course 1. So for both of the representations here we get the value 1 here. So 1 is to be multiplied to 1 by 2, the coefficients here. So finally 1 by 2 added to 1 by 2, we obtain the value 1 here, and this is of course to be represented in terms of beats per symbol. So this way we have just computed the entropy considering the case where the symbols are there in equal probability. Now the second case we have to validate. The second case is to have the computation of the entropy when the symbols or the gray labels are non-equiprobable here. So in the earlier assumption, to check the first case, we have to make a little modification. The little modification will be there, that number of probabilities of the occurrences of the zeros and that of the 1 will not be equal here, they will be of little bit change here. So we have the consideration small a is equal to the first row 1 1, the second row represented by the pixel values 0 1 here. So if you count the same, you see there are only 1 times the gray level represented by the 0, whereas 3 times the gray level represented by the value 1 here. So you see the probability of occurrences of 0 and 1 are not the same here. So this is what the second case, that we are not having them equiprobable here. So the step 1, just to have computation of the probability of occurrences, here we write in words probability of occurrence of the gray level 0. It is denoted by P of 0, and that value is only one time we have this 0 out of the total 4 pixels. We have the order 2 by 2. So we have it by representation 1 by 4 here. Now in the second one we have probability of occurrence of the gray level 1, that is given by, we have total 3 occurrences out of the 4 values here. So P of 1, this is equal to 3 divided by 4. So after knowing the probabilities of occurrences of the gray levels, we have to make computation of the entropy. See the entropy, here it is denoted by H of S here. So what is the formulation to have computation of H of S? Yes, of course we have used the same formulation, that is in terms of the probabilities of occurrences here. Here it is the formula. H of S is equal to, we have the summation I is equal to 1 to capital N P suffix I in multiplication to the logarithmic form of 1 upon P suffix I, where the base of the logarithm is equal to 2 in the binary notation. Here it is there. So this entropy we shall obtain in terms of bits per symbol here. Now in this second case where there is no equiprobability here, the probability of occurrences are different here. If we have the computation of the entropy, we have to represent the summation operation like this. So we have the first term, the product of P of 0 to the logarithm of the ratio 1 upon P of 0 to the base 2 here. Now this is further added by the multiplication of P of 1 to the log to the base 2 of 1 upon P of 1. So we have both the values. For P of 0 we have 1 by 4. For P of 1 we have 3 by 4. So if we have substitution, you see the first term is substituted, P of 0 is equal to 1 by 4. In this place also here it is. And here P of 1 is equal to 3 by 4. Here also we have shown it. So this is of course going to result into the value as represented 1 by 4 log to the base 2 of 4, 3 by 4 log to the base 2 of 4 by 3 here. So we get the calculation as 0.5 added to 3 by 4 times log to the base 2 of 4 by 3. Finally we compute it to the value 0.3113, and when adding it to the 0.5 we get the resultant value of the entropy for the second case of non-equiprobability of the gray levels or the symbols, that is equal to 0.8113, and the unit of measurement is there bits per symbol here. Now if we have the comparison of the entropy that we have computed in this case having non-equiprobability of the symbols to the entropy that we have computed in the earlier case. So in the case 1 we had the entropy found to be equal to the value 1 bit per symbol, whereas in the just previous case, case number 2 of non-equiprobability, the entropy is found to be the value 0.8113. Now you compare the two, which one is greater? The entropy that we have obtained into the case 1 is the greater. Therefore we can make a conclusion that the entropy is maximum when the symbols are equiprobable. So this way we can just have the proof to whatever the statement we have been asked to prove here. So any example you can take, you can have the two cases of equiprobability and non-equiprobability, and accordingly you can have the computation of the entropy, and after comparison you can have a simple conclusion, and you obtain entropy is maximum when the symbols are equiprobable here. So this was all about the part D solution of the problem statement number 1. So after the problem statement number 1, we will have a practice of another problem that is of course again related to the image compression model and usually asked into the examination. So let us have the statement for the problem 2 here. So in the problem 2 as well, we have the multiple parts here. Here we have the first part as represented by capital A here. So in the first part of the problem statement, we have been asked to have calculation of the efficiency of the Huffman code for the given symbol whose probability of occurrences are already provided in the problem statement. So this is what the problem statement. Calculate the efficiency of Huffman code. Huffman code is very popular. With the help of this type of the coding, we are actually trying to have the reduction of the redundancies, so that with the minimum number of the bits per symbol, we can have the communication of the image information and the storage as well. So it is what the image compression here. So Huffman code is very popular here. So we have been asked to have calculation of the efficiency of the Huffman code for the symbols provided in this particular table along with the corresponding probability of occurrences. Now you see there are 4 symbols in total, small a1 to a4. For small a1, we have the probability of occurrence to be 0.9. For a2, there it is 0.06. For a3, 0.02, and for a4 again 0.02. Now the thing is, the addition of the probabilities of the occurrences of all the events should be equal to 1, and yes, you can tally from the given data in this problem statement here. Now after this part A of the problem statement, we have been also the part B to this problem statement. Now in the part B, we have been given that for the image as just provided here, the computation of the degree of compression that can be achieved using, we have the two alternatives, either to work with the Huffman coding of the pixel values, and the second run length coding with the assumption that 2 bits to represent the pixel value and 2 bits to represent the run length here, and the given image sample is of the order 4 by 4. So the first row pixels are 3332. In the second row we have 2333. In the third row we have 3222, and in the last row we have 2110 here. So this completes our problem statement. We have only two parts to the second problem, part A and part B. So we get back to the part A. In the part A, we require to compute the efficiency of the Huffman code for the given symbols. There are 4 symbols with the probability of occurrences 0.9, 0.06, 0.02, again 0.02 here. So let us have answer to this part A here. So we shall have the total 2 steps here. In the first step, we will try to have a construction of the Huffman type of tree here for the coding purpose, and in the second step we shall have the computation of the average length, and finally we compute the entropy and the efficiency of the Huffman code also. So the first step, here we have construction of the Huffman tree here. So we shall arrange the symbols into the order a1, a2, a3, a4. Then the corresponding probabilities of the occurrences, we have 0.9, 0.06, 0.02, again 0.02. Then we have the several steps to get to a single value, and further we can have a coding with the binary digits here. So here we have the tabulation of the step number 1. So we have the total symbols arranged into the first column a1, a2, a3, a4 along with the corresponding probabilities of occurrences here. So now we have the representation like this. Now as per the Huffman tree, what we have to do, we have to denote the last 2 entries by 0 and 1 here. Further we have to add them and represent into the next step like this here. In the next step we have the coding by 0 and 1 to the last 2 steps here. Then further we also have to add them so that we get back to the value here like this, and again we have to provide the coding here. So here if we have the collection here, the final code for the symbol A1 it will be equal to 0, for A2 it will be 10, for A3 it will be 110, and for A4 it will be equal to 111 here. So here the length of code can also be written in the last column here. We have only one digit, the length of code is equal to 1. We have two digits, length of code is equal to 2. We have three digits, length of code is equal to 3. And similar is the case in the last one here. So here we have the three digits and the length of code is equal to 3 here. So now after the construction of the Huffman tree here, we have to compute the average length. See, the average length we can denote it by capital L bar here. So capital L bar is equal to the summation k is equal to 0 to capital N minus 1 for the multiplication of p suffix k into I suffix k here. So here we have the probabilities of occurrences multiplied to the corresponding lengths here. So here we have 0.9 into the length of the code is equal to 1, then 0.06 into the length of the code is equal to 2, 0.02 multiplied to the 3 for both the last cases here, and this calculation gives us 1.14 expressed in terms of bits per symbol here. Then we have to compute the entropy here. So here we have the formulation of the entropy. In this formulation that we have earlier also utilized here, we have to just substitute the probabilities of the occurrences here, and then we can have the computation of the entropy here. Now for the current case, we have the computation of the entropy as denoted H of S, and this is equal to minus the summation k is equal to 0 to capital N minus 1. We have pk log to the base 2 of pk here, and here we express in the 4 terms here. So here we have the corresponding representation 0.9 into log to the base 2 of 0.9 here, 0.06 into log to the base 2 of 0.06, 0.02 into log to the base 2 of 0.02, and same is the case in the last term as well. So this is giving us the value. Here we have 0.606 expressed in terms of bits per symbol. So from this value of the entropy, let us check the efficiency of the Huffman code. The efficiency of the Huffman code can be denoted by the symbol eta here, and it is basically the entropy divided by the average length of the coding here. So the entropy just now we have derived, we have computed in the previous step here, so that we put into the numerator that it is 0.606, and we have to divide it by the average length. The value is 1.14. So this ratio comes out to equal 53.15 in terms of percentage. So this is what the solution here, the solution to part A here, and from this particular solution the fact can be noted down that the Huffman coding requires at least 1 bit per symbol to transmit the source here, and also the Huffman coding is optimal at the block level and it is not optimal at the symbol level encoding here. Now we have problem number 2, part B here. So for this part B we have to find the solution. Just recall back what is the problem statement of the part B here. So for the part B, we had the statement for the image shown below, compute the degree of compression that can be achieved using the two types. First one is the Huffman coding of the pixels values, and second one the run length coding. Assumption is that 2 bits to represent the pixel value and also the 2 bits to represent the run length here, and this was the image sample of the order 4 by 4 here. So let us have the solution to this part. So from the given image we have a clarity that the maximum value of the gray level represented into the matrix is equal to 3. Because if you check into the matrix here, we have total 16 entries, and we have a single times 0, 2 times 1, then we have 3 times 2, and no, we have 4 and more to 6 times 2, and rest of the entries are filled up by the value 3 here. So the maximum value of the gray level to represent in the image pixel is equal to 3 here. Now we require to have encoding. So for encoding this maximum value, minimum of the 2 bits is required, and totally the 16 pixels here we have in the 4 by 4 order matrix representation for the corresponding image plane here, and here we have the total 16 entries in the given matrix, that is why. So this implies that a minimum of 16 by 2, so 16 by 2 is equal to 32 bits are required to code the given image sample here. So let us have the first type, the Huffman coding, and then the run length coding here. So here we have the Huffman coding of the pixels here. So for Huffman coding of the pixel, we have to of course form the Huffman tree here, for which we require the probability of occurrences of the pixel values or the gray values to be known here. So in the very first step, we shall have the computation of the probability of occurrences of the pixel values, then the formation of the Huffman tree here, and then we shall have the coding into the tabulation here. So let us have the first step, probability of occurrences of the pixel values. So here we go for the probability of occurrence of the pixel value, that is denoted by the value 0 here. So here we have P of 0. So as I have discussed and already you have seen in the problem statement, it is only a single time, the fourth row, fourth column entry. Hence we express the probability of occurrence of the pixel value 0 is equal to 1 upon 16 here. Now similarly we have to make a computation of probability of occurrence of the pixel value 1 here. So we have to denote it by P of 1 here, and as you see there are only 2 times the 1 here. We write the ratio 2 by 16 to be the probability of occurrence of the pixel value 1 here. Now we have the another gray level, that is with the value 2 here. So the probability of occurrence of the pixel value 2, that it is P of 2, we have 6 divided by 16, and the probability of occurrence of the pixel value 3 is equal to, we have 7 divided by 16 here. So this way for the 4 gray levels we have the corresponding 4 values of probability of occurrences here. Now we shall make the use of probabilities of occurrences of these gray levels to form the Huffman tree here. So according to the Huffman tree formation, we have to arrange the pixels into the descending order here. So here we arrange the symbol and the probability of the occurrences here. So in the decreasing order, we have the first entry with the value 3 here, the second entry with the value 2, the third entry with the value 1, and the fourth entry with the value equal to 0 here. The corresponding symbol probabilities here we denote. For the 3 it is 7 by 16, for the 2 it is 6 by 16, for the 1 it is 2 by 16, and for the 0 we have 1 by 16 here. So now the last 2 entries here we shall be coding with the 0 and 1, and to get into the next column we have to add the 2 probabilities of the occurrences here. So 2 plus 1 it will be equal to 3, and the total number of occurrences are equal to 16. So here we denote it as 3 by 16, and we carry forward the 6 by 16 to the next column as it is, and again code it as 0 1 here. So now here as the arrangement here we do, after the addition of the 6 by 16 to that of 3 by 16, we get the total 9 by 16, and that we put due to its the maximum value, at the first, and then we carry forward 7 by 16 at the second place here, and we code it as 0 and correspondingly 1 here. So this is what the formation of the Huffman code tree here. And now the coding we can note down from this Huffman tree formation here. So we have the code for the symbol denoted by the pixel value 3, and that it is equal to 1 here. Now next to that, the code for the symbol denoted by the pixel value 2 is equal to 0 0. Then the code for the symbol 1 is equal to 0 1 0, and the code for the symbol value 0 is equal to 0 1 1 here. So see, here are the corresponding codes to the symbols or the gray levels you can call. This is for 3, this is for 2, this is for 1, and this is for 0. So here we have the mean bits per pixel using the Huffman coding given by simply the summation of the index variable k for the multiplication of p suffix k into the length l suffix k here. So the mean or the average bit per pixel is given as 7 by 16 into 1 added by 16 by 6 by 16 into 2. Then we have 2 by 16 into 3 further added to 1 upon 16 into 3 here. So this gives us the numerator 28 divided by 16 here, and that is result into the value 1.75. So as per the problem statement, you recall back, in the problem statement we have been asked to make the use of 2 bits for the representation of the pixel value, and originally we are in the need of the 2 bits to represent the same, but through the Huffman coding we are in the need of only 1.75 bits to represent the pixel, that you can tally from the above step here. So therefore the compression ratio achieved through the Huffman coding is given as 2 divided by 1.75, that is what it comes to the value 1.14. So this you can note down. So this is what the thing for opting the case of the Huffman coding here. And after Huffman coding we have the second case to be tallied into the part B of the problem statement, and that one is to check the run length coding of the pixels here. So now for the run length coding of the pixels, by scanning the image from left hand side to the right hand side, and of course from top to bottom row here, we can write the run lengths. We have to denote it as 3, 3, 2, 2, 3, 4, 2, 4, 1, 2, 0, 1. So now here we have the two elements represented inside the bracket separated by the comma here. The first element in the bracket represents the pixel value, and the second element represents the number of occurrences this particular pixel value has occurred. So therefore here we use the 2 bits to represent the pixel value and 2 bits to represent the number of occurrences of the pixel value. So that is why the coding after the run length type here we obtain to code for 3, 3 we need 2 plus 2, that is equal to the total 4 bits here. To code for 2, 2 we need 2 plus 2, that is again equal to 4 bits. For coding 3, 4 we again need 2 plus 2 is equal to 4 bits. For coding 2, 4 we need 2 plus 2 is equal to 4 bits. For coding 1, 2 we need 2 plus 2 is equal to 4 bits. And lastly for coding 0, 1 we need 2 plus 2 is equal to 4 bits here. So totally we are requirement of the need of total 24 bits here. See, here are the 6 types here. So 4 into 6 times, here we have the total 24 bits here. So originally we were in the need of the 32 bits, and hence the compression that can be achieved through the range length coding, here we divide 32 divided by 24 here, that gives with the answer 1.33 here. So as a solution to the part B of the problem statement, the second problem is it was we have opted both the Huckman coding as well as the run length coding here, and accordingly we have found the solution to both of these. Now these were the two problems for the practice purpose I have taken here. Now I will just give you the brief introduction to what the image compression model, or in general the image compression models, our today's topic is there here. So image compression models here. See here, image compression is one of the fundamental step of the digital image processing here. With the image compression, we are having the representation of the same image information with the application at hand and having the minimum number of the pixels in general, we have to say here. So the image compression, the first two words from this particular title if you take, so image compression techniques are basically having a reduction or the compression of the amount of data that is required to have the representation of the image here. So basically, while having the representation of the image, there is a certain portion that is not at all to be saved for each and every case. It can also be reconstructed here. So that kind of part which is not so much important, we can call it to be the redundant data here. So the reduction into the redundant data is nothing but the compression here. So this is what the image compression here. So the typical image compression techniques, if you talk about, we have a combined form of the three individual things that forms the image compression system that I am going to visualize you people in the block schematic form here. So let us begin to have examination of the overall features, or you can also say the characteristics of such image compression system, or our today's topic, image compression model, and to just develop a general model to have representation of the same here. So let us have a figure that shows the compression system that consists of the two distinct structural blocks, encoder and decoder, and this is what the very important and of course simple and straightforward image compression model here. Now you see here we are talking about the two blocks. The first block that we have said it to be the encoder, you see, and the second block we have talked about, here it is decoder. So as you come from the left hand side, you see there it is the input of f of x comma y. So what is f of x comma y? F of x comma y is the original image. See, the original image is fed as input to the block encoder. This encoder is further giving the output to the block that is called as channel here, and through the channel further it is fed as input to the decoder, and finally at the right hand side we are obtaining f cap of x comma y. F cap of x comma y is the reconstruction image here, reconstruction image. Now what is there inside the encoder and decoder details definitely we shall see here. See, the encoder here, it is basically the source encoder plus the channel encoder. For the decoder again we have the channel and the source decoding in the two blocks in the corresponding things here. So this is what the simple image compression model. We are going into the more details as well. So already I have made it clear that the input image is represented by f of x comma y is given as the input to the encoder block. So here it is source encoder plus the channel encoder. So what the encoder does, it will create a set of symbols from the input image, that it is f of x comma y here. Now after transmission over the channel, the encoder representation is fed to the decoder as I have discussed, and we are obtaining the reconstructed output image denoted as f cap of x comma y. So as you compare f cap of x comma y, it may or may be the same or the different as you compare to the original information. that it is denoted simply f of x comma y here. Now this is what the flow from the original image. We have to go through the encoder, source encoder, channel encoder, then the exact communication channel, further through the source and the channel decoding system here, and certainly obtaining at the end the reconstructed image here. So if this all image compression system is error free, it is not making any kind of losses here, it preserves the information, so some level of distortion is practically present in the reconstructed image here. That is why we have said that it is not always the replica of the original image. Both the encoder and decoder, what have been shown into the previous figure, consist of the two relatively independent functions or the sub-blocks. Those we have called it to be the source and the channel. For the encoding part, you see we have a source encoder that removes the input redundancies and the channel encoder that increases the noise immunity of the source encoder's output here. Now on the right hand side, you have seen a decoder block that includes first of all the channel decoder, then the source decoder here. So if the channel between the encoder and decoder is noise free, the channel encoder and decoder are omitted. It will be simply the source encoder and source decoder that will constitute the complete image compression system here. Now we shall have more details with respect to the exact source encoder and the source decoder here. So basically, what is the responsibility of the source encoder? Source encoder is responsible for carrying out a reduction or the elimination of any of the coding type, the interpixelity or the psychovisual redundancies into the input image here. Now this particular approach can be modeled by a series of the three independent operations we see into the block schematics again. So these are basically the mapper, quantizer and the source symbol encoder here, and figure A that is describing this particular approach here, and we have the figure B also that depicts the corresponding source decoder here. So here we see in the block schematic on the left hand side we have f of x comma y, the original image here. So it has been fed as input to the mapper that further feeds it to the quantizer and lastly to the symbol encoder here, and thereupon we feed it over the channel for communication here, and from the channel here we obtain it to the symbol decoder stage, then the inverse mapper, and here we have f cap of x comma y, the reconstructed image here. So see here in the initial block diagram I have shown you the original image is fed as input to the source encoder, then channel encoder, then the channel, then we have channel decoder, source decoder and the reconstructed image. So what is there inside the source encoder? The three blocks here you see. And what is there in the source decoder? The two blocks here you see. So these blocks you can add into the previous block schematic also. The number of blocks with more details you can see separately here. So as you see the figure A, the upper figure here, the first stage of the source encoding process, the mapper transforms the input data into a format designed to reduce the interpixel redundancies of the input image, and this is the operation generally of the reversible kind here and may or may not also reduce directly the amount of the data required to represent the image here. Now we have for example the run length coding for the mapping purpose that directly results into the data compression in this initial stage of the source encoder here. The representation of the image by the set of the transform coefficients is just the example of the opposite case, and here the mapper transforms the image into an array of the coefficients, making it interpixel redundancies more accessible for compression in the later stages of the encoding process here. Now you see the second schematic, block schematic, here in the second schematic we have the quantizer block into the middle here that reduces the accuracy of the mapper's output in accordance with some pre-established fidelity criterion here, and this stage particularly reduces the psychovisual redundancies into the input image, and this is the operation that is irreversible type here, therefore it must be omitted while we are having the lossless or the error free compression here. Now we have the third and the final stage of the source encoding process, where the symbol coder creates a fixed or a variable length code to represent the quantizer output and maps the output in accordance with the code here. So here we have the term symbol coder that distinguishes this coding operation from the overall source encoding process here, and in most of the cases a variable length code is used to represent the mapped and the quantized data set here. Now you see, this assigns the shortest code words to the most frequently occurring output values and thus reduces the coding redundancy, and the operation is of course reversible. The source decoder that we see in the down, that contains only the two components, a symbol decoder and the inverse mapper here. So these two blocks perform in reverse order the inverse operation of what the source encoder has done here. Because the quantization results into the irreversible information here, and an inverse quantizer block is not included in the general source decoder here. The channel encoder and the decoder play a very important role in the overall encoding decoding process. When the channel is noisy to prone to the error, they are designed to reduce the impact of the channel noise by inserting a controlled form of the redundancy into the source encoded data, and as the output of the source encoder contains the little redundancy, it would highly sensitive to the transmission noise without the addition of the controlled redundancy here. So here we have one of the most useful channel encoding technique that was basically found and devised by the R.W. Hamming. We generally call it to be the Hamming code here. You see, this is very simple. This is basically based on the appending of the enough bits to the data being encoded to ensure that some minimal number of the bits must change between the valid code words here. Example, here we take, if 3 bits of redundancy we add to the 4 bit of the code word, so that the distance between any two valid code words is equal to 3, and all the single bit errors can be detected and corrected here. So here we have the representation, for example, for the 7-bit Hamming denoted 7, code 4 code here. So here we have H1, H2, H3, H4, H5, H6, H7 in total. These are associated with a 4-bit binary number. We have B3, B2, B1, B0 here. So these are, we have the computation of the H1, H2 and H4 just by having the logical operation, that is exclusive OR operation in between B1, B2 and B3, whereas H3, H5, H6 and H7 are correspondingly the individual codes to represent B3, B2, B1 and B0 here. So now H1, H2, H4 are not wanted there, but they have been coded as such so that the information will not be lost here. So here we have the bits H1, H2 and H4 of the even parity bits for the bit fields. We have B3, B2, B0, B3, B1, B0 and B2, B1, B0 respectively. So to decode a Hamming encoded result, the channel decoder must check the encoded value for the odd parity over the bits field in which even parity was previously established, and a single bit error is indicated by the non-zero parity word. We have C4, C2, C1, where we have the denotation of C1, C2, C4 like this by the exclusive OR operation between the H1, H3, H5, H7, then H2, H3, H6, H7 and lastly H4, H5, H6 H7 here. So if a non-zero value is found, the decoder simply complements the code word bit position indicated by the parity word, and the decoded binary value is then extracted from the corrected code as H3, H5, H6 and H7. So this was all about the details of the channel encoder and decoder along with the source encoder and decoder, which are a part of the image compression model that we have discussed, and we have also the practice of the two problems based on to the coding for the image compression purpose here. So I hope your doubts are definitely got cleared here. We shall meet into the next week with another topic from our image processing subject.